Okay, good morning all. So we will now discuss about the next classifier model in the supervised learning approach, that is called as a support vector machine. So support vector machine classifier is a classifier which mainly classifies the data based on a hyperplane. It is also otherwise referred to as maximum margin classifier. So the metrics that is very popularly used in support vector machine classifier is called as a hinge loss on hinge error. So we'll discuss about this classifier detail. So support vector. So basically this classifier takes care of the vector representation. So if you have a binary classification comprising of two classes, mainly yes or no, true or false, male and female. So the vector representation of this classifier takes a vector representation to classify them into two vectors. So two separate classes. So any item to be classified can be represented as a d-dimensional real vector. So this is the specialty of this classifier, where the previous classifiers that we have dealt with deal with only the scalar representation, because they are primarily either probabilistic based or distance metric based, or they are based on the attribute selection features. So if you look at the decision tree or naive based classifier, that's probabilistic based, then followed by the k nearest neighbor, that is distance metric, whereas support vector machine is primarily based on the d-dimensional real vector, because this considers the data points to be vectors, and the classification carried through the d-dimensional real vector is considered as support vector machine classifier. So the task here is find a linear classifier. So there's also otherwise called as a hyperplane. So it's basically a diagonal line that we usually draw in the linear regression or linear classifier, where we separate the data into two separate classes that divides the Euclidean space into two parts. So two-dimensional example training set primarily comprises of a task where you separate it by a line. So any of these linear classifiers would be fine, but which one should we consider as the best? Because ideally the distance between the blue dots to the red dots is very much clearly possible to demarcate into two separate classes, but that's not the situation in the real world, because what we notice is that the data is spread all over and you have non-uniform distribution of data. So if that is the case, some of these red dots might be occurring on the blue side and blue dots might be occurring on the red side. So by just using a single diagonal line, it is not always possible to separate them into separate classes. So that's where the support vector machines come handy, and they help us classify the data. So what line is better? So ideally, in order to measure the quality of a linear classifier by its margin, the margin actually what we are referring to is the width that the boundary could be increased without hitting a data point. So considering if you want to create set up a wall between the red and the blue data points, what are those data points which will actually fall on the boundary of this wall, or so called the hyperplane or the maximum margin classifier? Okay, so these data points that you are seeing that falls exactly on the boundary of your classifier or the hyperplane, they are referred to as support vectors. So the d-dimensional vectors that are used to support your classification process are referred to as support vector support vector machines. So the wider the margin, the better. Lesser the margin, the less is the possibility that your classification can be erroneous. So support vector margins is decisive based on the data points, um, how many data points are close or exactly fall on the boundary of your margin. If you already see for a particular margin size, the data points are already existing on the boundary size, then that should be your ideal margin width. Okay, so in this case, if we increase the margin on one side and reduce the margin on the other side, because the data point is already on the boundary, uh, whereas on the other hand, the data point is also on the boundary. So the margin of the hyperplane or the classifier is pretty much very important in classifying the data. So this is also otherwise called as a maximum margin classifier. The reason is a linear classifier with a maximum margin. So the margin size of your classifier or the width of your hyperplane will determine how well your data points can be classified. So while carrying out this process, we also encounter a very typical type of error which is similar to like opening a door. Okay, doors typically have hinges which will keep the main wood intact to the door. So as we open the door and close the door, we often have certain portion of the data that is included in certain portion of the data that is not been touched upon. So that creates what is called as a hinge loss. So that is one of the major that is the loss that the SVM has to look at. So maximum margin classifier, the simplest kind of the support vector machine. Uh, so the data points that the margin pushes against are called as the support vectors. Now that it's always in such a classifier that the training set is linearly separable. So it is not always possible to separate the data points using a linear diagonal or a linearly separable situation, because in real world the data is non-uniformly distributed and you will see data points spread all over. So drawing one single line is not all possible, because you might see blue dots coming with green and green dots joining already mixed up with blue dots. So it is intuitive to divide two classes by a large margin, because larger margin guards best against small errors. That is, we are trying to reduce the error so that we have maximum number of data points lying on the boundary of the hyperplane. So this approach is robust because it usually uh, it tries to control the fraction of it tries to account only a small fraction of all data points rather than a big set of data points. So there are some theoretical arguments when considering the margin. Empirically, it works very well. So at the beginning, we assume that our training data set is linearly separable. But there is a problem that if you notice here, the blue dot is actually sitting in among the red. Similarly, there could also be a situation where a red dot sits among the blue dot. So in this case, if you draw a diagonal line separating the blue and red, you still have an error, noisy data point which is still lying within the red dot. So we call something called as soft margins can be used to handle such cases. So which allow the classifier to make some mistakes on the training data. So each misclassification gets assigned an error. So total classification error can then be minimized. Total classification error can be minimized. So this is what we refer to as soft margins. Okay. So soft margins. So at the beginning, we also assumed that there are only two classes in training set, how to handle more than that. So one versus all classifiers. So building a support vector machine for any class that occurs in the training set to classify new items, choose the greatest margin size. So in case if you notice that there is more than one versus all classifiers, if you have to classify more number of data points, then you have to look at the misclassification error by increasing the margin, greatest margin class. So one versus one classifier. So if you have to build a SVM for any pair of classes in the training set, to classify new items, choose the class selected by most SVMs. Okay, multi-class SVM. So all these are evolving ideas that people have tried using SVM. But one very common and general practice of improving the SVM model is controlling the hinge loss, right? So we will discuss about that next. So the intuition of hinge loss is a loss function used for training the classifiers. It is used as the de facto maximum margin classification for support vector machines. So if you see this picture, so if you move this hinge loss to move the hinge loss in this direction, let's say now I want to move this in this direction, right? So this diagonal movement from this side to that side, so or you are moving the data points to this side, so either of the two cases, so this diagonal movement and this diagonal movement, either of the two cases will actually contribute to hinge loss. So the penalty or the loss size will be lesser when the hinge loss is moving towards a correctly classified category rather than the hinge loss moving towards incorrectly classified categories. So in these two cases, the hinge loss can be can account for the accuracy and the performance of the SVM model. So x-axis represents the distance from the boundary of any single instance, and y-axis represents the loss size or penalty that the function will incur depending on its distance. So if you put a penalty or loss size considering if the hinge, if the SVM tries to increase its margin towards way beyond 0, then it becomes incorrectly classified. If it heads close to 0, then it becomes correctly classified. So this is the one loss factor that we should take into account when dealing with SVM. The qualitative description of hinge loss says that when a data point's distance from the boundary is greater than or equal to 1, the loss size is 0, right? If the distance from the boundary is less than, if the distance from the boundary is less than 1, then we incur a loss. So at 0, the distance, the data point is on the boundary, then the loss size is 1. So if you correctly classified points will have small loss size, while incorrectly classified instances will have high loss size. So high hinge loss indicates the data points being on the wrong side of the boundary, hence are misclassified. So as I was discussing earlier with the picture, so if the hinge loss or the hyperplane margin, maximum margin classifier tends to go beyond, tends to wave towards a point outside 0, then it actually contributes to more loss than compared to waving towards 1 or close to 0, where the hinge loss will be a lot lesser. So while a positive distance calls for low or 0 hinge loss and correct classification. Okay, now let's see one problem related with linear SVM. So let's consider a case of binary classification starting with data of 8 tuples as shown in this table. So we have x1, x2, sorry, a1, a2 with y with +1, -1. So either of positive class or a negative class. And lambda is the learning rate threshold or the support vector that we have provided for this data. So we have identified two support vectors for the training data. So one is for the positive class and the other one is for the negative class. Now using this data, we have to identify under which class test data falls under. So note that only the first two tuples are support vectors in this case. So we apply the formulation like this. So W, we are considering W1 and W2, two data points, A and B denotes a parameter to be determined. So we can solve for W1 and W2 as follows. So first we will take the support vector on the positive side multiplied by 1 multiplied by the A1 multiplied by A1. So that is 0.38, then followed by plus the support vector plus the support vector multiplied on the negative on the negative class multiplied by 0.49. So first we have to take the support vector multiplied on the positive side multiplied by 0.38, then followed by the support vector on the negative class multiplied by 0.49. Okay. So W1 turns out to be minus 6.64, and W2 in the same manner we do it for the next data point also, that is positive class multiplied by 0.47. This is for A2. Positive class multiplied by 0.47 and negative class multiplied by 0.61. So, uh, so W1 gives minus 6.64 and W2 gives minus 9.32. Now we substitute these two values and on the graph to visualize how the support vector hyperplane actually looks like. So when we visualize this on a linear SVM scale, then we see that tuples belonging to the positive class to tuples belonging to the negative class. So if you populate A1 to A2 on zero point 0.2 to 1 scale on x and y axis, then we notice that the hyperplane turns out to be like this. So minus 6.64 x1 minus 9.32 x2 plus 7.93 plus 7.93. So this 7.93 is coming from your data, is the value that is been provided. So uh, so considering this projection of the hyperplane, now we have to determine the parameter b can be calculated for each support vector as follows. So b1 and b2 is what we have to find. What is the support vector x1 and x2? Support vector x1 and x2. So 1 minus w times of x1, 1 minus w times of x2. So 1 minus w times of x1, that is minus 6.64 into 0.38 minus of 9.32 into 0.47. So what the value that we are getting here is so 1 minus 1 minus minus 6.64 that we got in the earlier into x1. So x1 here is 0.38 and x2 is 0.49. X2 is minus of 9.32 minus of 9.32 multiplied by 0.47. So 0.47. So we are considering these two parameters for W1 that we have obtained. Similarly, you will have to consider these two for W2 that we have obtained. Okay. So after this, using the dot product, we get this value 7.93. So ideally, it is minus 6.64x minus 9.32x2 plus 7.93. So the 7.93 value that we are getting is from these two, B1 and B2 support vector. So averaging these two values, B1 and B2, we get B is equal to 7.93. So thus the maximum uh, um, maximum multiplier. So the maximum classifier for the maximum maximum multiplier, the maximum classifier, maximum margin, the maximum margin hyperplane can be defined as minus 6.64x1 minus 9.32x2 plus 7.93. So that is equal to 0. Suppose the test data that is been given to you where x is equal to 0.5 and 0.5, and if you substitute the derivative of x, then we can find that w of x plus b, w of x plus b. So x here is going to be substituted with 0.5. So 6.64 into 0.5 minus 9.32 into zero point 0.5 plus 7.93. So it turns out to be minus 0.05. So it's a clear indication that this test data, whatever you have provided, falls under negative class. So first you have to identify the linear SVM and its hyperplane from the given data. Since here only two support vectors are given, it is also possible that in your actual problem there might be some other problems where more than where there can be multiple support vectors. So here in this case only two support vectors are taken to formulate the hyperplane, right? So you will have to consider uh, uh, all these support vector points and then perform the computation by taking into account the x and y coordinates and the class to which these support vectors belong to. Okay, the class to which these support vectors belong. So once you have identified the W1 and W2, then you have to substitute them into the expression. Then you also have to find out B, because W1 is equal to lambda, that is a support vector, lambda I yi into xi plus B. That is how the equation goes. So lambda I yi into x2 plus B for W2. So B is the value that you have to identify. So B will be the parameter used to calculate uh, at what a point of the support vector is, where does the support vector for x1 fall, where does the support vector for x2 fall. So that can be calculated by just simply subtracting 1 minus x w of x1, 1 minus w of x1. So w of x1 is your value that is given in the data set, and w is what we have found, and then the w2 of x1. Similarly for w of x2, then w of x2. Okay, so these two values, once you find out the dot product of these values and then you average b1 and b2, you get the b value. So this value will be added to the weights that we have identified. So w of x1 plus b, okay, that will give you the derivative of x, so this that will become the um, maximum margin hyperplane. Maximum margin hyperplane is defined in this manner. So once you formulate this equation, then whatever the test data that is given to you, x equal to x and y, those values you have to substitute in the derivative of x. Then you will identify to which class this given test data belongs to. So as in this case, the outcome that we are getting is negative. So hence we can say that this implies that the test data falls or falls on or below the maximum margin hyperplane, and SVM classifies that x belongs to the class label negative. So it belongs to the negative class label. Okay, so this we can identify. So there are issues very commonly uh, possible while performing this SVM classifier. One of the common problem is overfitting scenario, because if you try to run this SVM, try to control the loss and then increase the SVM proximity by increasing and decreasing the margin, you end up leading to a situation that the model's performance can become overfitting. So if we are mapping to high dimensional space that is complicated enough, okay, so we could find a perfect linear separation in the transformed space for any training set. So how to separate this data into two parts, because blue and red, they are actually going in the other sides of the classes. So in this case, cross validation is one good help to overcome the overfitting scenario in SVM. So we randomly split the available data into two parts, training and test sets. Use the first part for learning the classifier and the second part for validating the classifier's performance. Choose a classifier that maximizes the performance on the test data. The other technique that we could also apply is regularization. That is, if you know how a good classifier roughly should look like polynomial or Gaussian, right? So based on what kind of landscape your data actually looks like, accordingly, if you select the required classification approach, you could introduce a penalty value into the optimization problem also. So the hinge loss that we are discussing can actually introduce a penalty value which will try to control the hyperplane as the margins of the hyperplane as close as possible, so that the hinge loss can be controlled. So assign a larger penalty if the type of classifier is far away from what you expect, and a small penalty otherwise. Choose the classifier that maximizes the overall optimization goal, because optimization will help us improve the performance of the classifier. So example of regularization is soft margin technique, since classifiers with large margins and few errors are mostly preferred. Okay, classifiers with large margins and few errors are mostly preferred. Okay, so with this I come to the end of this presentation. So we have discussed about SVM and its implementation details, and we have also discussed about the hyperplane, and then we also discussed a problem on the linear SVM, and then what are the challenges with SVM, especially when the model deals with complicated data or data with combination of classes which are spread over all over. So the two possible techniques that we could apply to control overfitting are cross-validation and regularization. Okay, so with this I conclude this session.